Okay, sorry for the delay. Apparently I forgot the sheet and have to walk back for it. Okay, so now I think we are ready. Apart from the fact that I will be panting a little bit. Okay, but nevertheless, well, we carry on from yesterday. Yesterday we studied about cables accepting point loads or concentrated load. Today we look at it if it take the distributed load. Okay. Well, since the introduction was done yesterday already, I'm just going through it quickly. The cable that we actually look at, that distributed load, we will talk about the application first. Again, we go through quickly, and then we start to formulate how we actually gain equations to calculate the forces inside the cable itself. In this case, of course, tension. Okay. Then example. Notice no S this time. There will be only one. Okay. I'm not really sure. It might be quite short, it might be quite long, depending. But I suggest if you got lost somewhere, could you get down the flash? Thank you. Okay. I suggest that if you don't understand the equation during the proof, which is quite confusing, please ask. Because as you already realize, this proof will come out in the exam as well. Okay. So getting to understand it is quite important. Application. We study this purely because we want to do some kind of structure that rely on staying on the cable, right? The application like yesterday is a bridge staying on the cable. Okay, very long span. Like that, the Golden Gate Bridge. Somewhere in America as well, I think. I don't know what it is. Okay, another bridge. It's just in Thailand we have the Lamanai Bridge. It's also cable stay. Okay, this type of bridges will rely back on this same principle. The detail may be slightly different again because we don't take all accounts in this course yet. This is again a basic knowledge. You will study this one again in maybe your master degree. I don't think we usually teach it in a bachelor degree either. Okay, bridge design will be one of the could be elective in the fourth year. Okay, if the lecturer feels up to it. Okay, the schematic we showed yesterday, basically the one that take the load. This is the floor, this is the road. Okay, the load will go down to the road. The road itself doesn't take the weight. The weight transfer up to this horizontal cable, vertical cable. Sometimes called suspenders, sometimes called secondary cable. Right, the one that is vertical. Then it transfers up to this main cable. Right, just for the feel of it. In this course, we look at only the force that happen in the main cable. Secondary cable will be in more details in other subjects. Okay. Well, this is okay. Oh, hang on. We can look at any part of the cable. We end up with the same equations. Okay. However, just to be more general, I would look at the one that has two support up in the level and then coming back down, going back up the cable. Okay. Now, just to make it more general as such, we talk about a cable that is not supported at the same level either. Okay. That one signifies the support on the column. That one is another column. This is the floor. The load will go down to the floor, transfer by that secondary, the suspenders to the main cable. Okay. Now, before we go on, let me be clear about oneself. Last time we see it, when we have point load acting on the cable, it becomes a straight line. Correct. So basically, this cable, because the secondary cable carry it up here, here, and here, and here on the point. So basically, it's actually a straight line, right? But we know that if it's small enough, this line, if they are small enough, compared to the whole length of the cable will be considered an arc anyway, a curve anyway, right? You look at the bridges, like the picture we just showed. You look at the Lamanai bridge. This main cable always in the curvature, not segmental straight line. Okay, so we will treat it as if it is a curvature. The idea is that if you put down the suspender closely enough, it won't seem like the whole distributed load go up to the cable itself. Okay, so when we calculate this cable, we look at as if this distributed load at the bottom, this one will include the weight of the load itself as well. We'll go straight to the main cable up here. Okay. Now, before we start, because apparently when we start designing it, we don't know the shape of this cable. So to start off with, we'll find out some place that where we can start coordination of XY. In this case, the reason will be clearer later, but we actually choose the lowest point in the cable. Okay, so if that is the lowest point in the cable, we don't know where. Okay, we will have to find it later. Okay, then we'll set up our XY there. Okay, let's start off with. Then the next thing is that once we set, because we don't know anything about this cable, the only thing we know is that W could be described as a function of horizontal distance. It could be a constant, it could be a linear function, it could be curve parabola, could be sine wave, we don't know, but we know that we should be able to describe it with x, right? If we can describe it with x, we have to know where x starts, right? The reason will be clear later why they set it down here. Okay. Now, basically, if we set origin at the lowest point of the cable, x0 here, y0 here, and we start measuring x from this point on, to the right hand side positive, to the left hand side negative, y upward positive, y downward negative. Okay, just normal coordination. Then we will look at small element of the cable. There, we will cut it off. And what we want to know is what happened to the internal force in this cable, in this small segment of the cable. Again, I repeat myself, we will assume that W act directly onto the cable. Okay, so if I draw the free body diagram of these small pieces, this should be the picture we see, right? This is the curvature, the cable, the main cable. W act directly on the, W act directly on the cable, correct? Now, notice that I haven't put in any force yet. If that distance we call dx, small change in x, that distance should be small change in y, correct? So we call it dy. Okay? Now, I will draw tangent line, two tangent lines. Do you know what tangent line is? Yep, it's เส้นสัมผัส. Okay? One tangent line I will draw on that point, one tangent line draw on that point. Notice the cut. At the cut is an angle, right? There's no horizontal vertical line here. So it will be something like this. The reason I have to draw the tangent line is that the axial force we know that has to be on the same line as the member. It was quite easy to draw at the beginning so far because our member tend to be straight line, correct? This one here is not a straight line. So the tangent will be on the same line as the member at the cut point, which we have to rely on this tangent line or the เส้นสัมผัส thing to know the direction, right? So therefore, at this cut, we know the cable doesn't have shear force, cable is a rope, right? The same mechanic, only tension. Cannot be even compression. Okay, axial force, that is tension only. So at this point, we will have one tension, and that one another tension, correct? At the cut point. Notice direction will change according to the alignment of the point you cut. Okay, since our x starting from left to right, that one should be the beginning one. That one should be the end one. Okay, if we say the beginning is equal to t, that one should have changed the value, or we think it might change the value. So that one will be equal to the same value of t plus any change it might happen. And what we will do is we will find that change if we can. Okay? Before we move on, because this is about mechanics, it's about forces. You can guess there will be sigma fx, sigma fy involved. Right? Because these forces are not horizontal, are not vertical. So we have to talk about the angle. Okay? The same thing because it could be any places. So I will name the starting angle theta. But you know that is a curvature, meaning the angle will keep changing, right? So this point here then it no longer theta. I will say it's equal to theta plus any change might happen during this distance. Again, this is a small distance. Any change should be small. That's why we say dt, small change in tangent, tension, sorry. And d theta, small change in the angle theta. Okay? And this part is okay? Or are you confused about something? I can explain again. Okay. In that case, if it's small enough, we can assume that w, the function of w could be estimated a straight line. Okay. That's normal drawing. Now, I get this element and I want to focus on that element. So I get rid of the main picture for now. When I need to use it, I will bring it back. But it's going to be quite a long time before we go back to there. Now, once we know, well, we don't know the force, but we can actually put in symbol for forces and the angles. So maybe it's time to start doing something about the equilibrium. Don't forget our bridge doesn't move. Our bridge should be there, right? Should stay there. So this small element has to be in equilibrium as well. If it is in equilibrium, sigma fx must be 0. Okay, normal component taking. That one into horizontal, you use cosine theta. Correct? Going to the left, let's say negative. There. That force is T plus dt. Get component into this one. The angle is not theta. The angle is theta plus d theta. So that is the whole term. That is the whole force T plus dt. That is the whole angle theta plus d theta. It's just not easy to manipulate or to arrange it. However, this morning I don't know what to do because I can't remember the equation, so I search in the internet and I find out this equation. I think it's something to do with trigonometrical calculus, geometrical calculus or something like that. But whatever it is, this equation, as you see it. If I ask you to prove this part, this equation will be given. I can't remember it. I don't have a large memory. I have a very small gigabyte, so I tend to have to be able to search it somewhere. Okay? So I don't encourage you guys to remember things. Anyway, once we get that, then we can manipulate that. Okay? Expand the term. Expand it, nothing. That one is the same one. That one, that term, cosine A, cosine B. Right? Minus sine A, sine B, there. As simple as that. Okay? Well, I think if we try to expand the term now, it will be very confusing and very long. So I will jump a little bit and then do one more thing first. We know that our theta is small, correct? The theta is really small, basically approaching 0. What is the rule when theta is really small? Then cosine theta will approach 1 and sine d theta will be about the same value as the theta itself. In this case, approaching d theta. As soon as I indicate this, we have to understand something. This theory isn't based on degrees. This theory only based on radians. So as soon as I state that, it means from this point onwards, if we talk about the angle theta, the calculation should give you radians calculation. Okay? That's just so that you know. Next, then we just say that since that is equal to 1, that term is just cosine theta. That term sine d theta is d theta. Just substitute to that. Correct? The next step, you have no choice then, I'm afraid. You have to expand it. The reason we have to expand it, because in this term, we can't manage it. We don't know what it means. It's always the case. You expand it and then shorten it or expand it and regroup them, right? So as a good calculus user, right, expert in calculus, so we start expanding the term. Nothing much, just two brackets timing each other, right? That term is that term, right? Then t times cosine theta, that term. T times minus sine theta, d theta, that term. Okay? And then dt times cosine theta, that term. Dt times minus sine theta, d theta, that term. Simple. Right? That one and that one become 0. Correct? That one stay, that one stay. That one, dt times d theta. dt is small, d theta is small, approaching 0, negligible. Okay? So in the end, we should have only these two terms left. There we are. And they are equal to 0. The reason I have to take bracket here is just so that we understand that this differentiation is only with tension, nothing to do with cosine theta. Meaning you differentiate tension and then time cosine theta, not t times cosine theta and differentiate the whole term. Okay, differentiation stay with t only, with tension only. Okay. I need more space, so I'm gonna move the last expression we have from bottom to top and getting into a new page. This one here, apparently manageable, but it needs one more transformation. This one doesn't mean anything in human language yet. So we consider this term. How do we get to this term? I think it's actually experience of the people who play with calculus a lot. Okay, so they know that it will equate to that term itself. Okay, so this is how it happened. You remember when you differentiate u times v. Remember that one? du times v, right? In bracket, d in bracket u times v. Then you have differentiation of u times v plus u times differentiation of v. Correct? The same thing happened here. Then that term is t times cosine theta, u and v, right? So the first one is when you differentiate u, leave v alone, and then plus when you leave u alone and then differentiate cosine, differentiate v. Okay. Now start to get similar. There, that term is that term, right? So we have to change that one a little bit more. Now this one here is differentiation of function. How do you differentiate a function? Ooh. If I have differentiate of cosine theta by dx, how do you get it? You use chain rule, right? Oh my god, I didn't prepare for this part, so I have to write on the board. D cosine theta by dx, that one is equal to d cosine theta by d theta times d theta by dx. Is that familiar? That is chain rule. Okay. Okay. So basically, I can expand that term there. Which term? That term, sorry. Right? In that form. Just ignore the x. Okay? So basically, d cosine theta will equal to differentiation. Oh, that one, sorry. That one is in fact minus sine theta. D theta dx. Correct? Therefore, if we ignore the x just to make it common term, then it will be d cosine theta equal to minus sine theta d theta. Right? That one to that one, is that okay? So this one meaning I can differentiate with y instead, with z instead. It's just open differentiation. Okay? Just not common term. So we agree on this one or not? Yes or no? Okay. I'm not really sure you nod your head because you are starting to get sleepy or what, but I think I will take it as a yes. Okay. So, meaning that I can change that form into what I just proved it. No, that change that one into that one. T remain T. Correct? Now notice that that one equal that one equal that one. Correct? Therefore, this whole expression must be equal to 0. In other words, that whole expression is 0. Right? So now, in fact, there is a human language explaining this. What is T cosine theta? T cosine theta is your component of the force in the x direction. Correct? D means the change. If it equals 0, then it means that the change in horizontal component of this tension is 0. Translate English into Thai. T cosine theta เนี่ยนะครับมันคือการแตกแรงเข้าหาแกน x ถูกไหมครับเพราะฉะนั้นแปลว่า t cosine theta เนี่ยก็คือไอตัวเขาอะไรไอตัวขนาดของมันในแนว x ไม่ใช่แนวรวมหรือแนว y แนว x เท่านั้นถูกไหมครับตัว d เนี่ยแปลว่าความเปลี่ยนแปลงถูกไหมครับมันเท่ากับ0นะครับเพราะฉะนั้นประโยครวมก็แปลว่าความเปลี่ยนแปลงของไอแรงในแนว x เนี่ยเท่ากับ0แปลอีกในหนึ่งก็คือว่ามันคงที่ครับTherefore, it means the horizontal component must be constant. Okay? If it's constant, then rather than leaving it with just, I don't know what we're going to call it, so they give it a name. Apparently, so many people have proved it, so many people have named it, so there are some names that they use. These are 3 of them. Sometimes they call tension in the x. Therefore, it's a Tx. Some people call it tension in the horizontal direction, so call it Th or Fh, or sometimes T or sometimes F. Okay? Apparently, it also equal to, I will explain later, it will also equal to tangent at the origin. The reason is because at the origin is the lowest point, remember? Meaning the tangent line is horizontal, meaning tension is on horizontal line. Since it's constant, therefore it is the tension there as well. So sometimes they call it not T0, but T at origin. Okay? Depending on the books, depending on who teach it. Okay, but it means the same thing. It means the component on the horizon, on the horizontal direction. Okay? So I like this one, so I'm going to use this one. Okay, and we set it as equation 1, meaning there will be equation 2 following. There. Let's go back, just right off the board. Move the equation we note down to the left hand side under the picture. Since we done sigma fx last time, you want to guess what we're going to do? Of course, sigma fy. Apparently, it doesn't get any shorter. It apparently gets longer. This time, in the vertical direction, we have that force, and that force. 3 of them this time. So it turned out in that way. Okay? That one comes from that tension into y direction, sine theta, downward minus. W dx downward also minus. That one come from that one, take into that side, upward positive. The angle is theta plus d theta. So sine the whole angle. Well, I think we should start using that again. Again, I searched one this morning as well in the internet. Okay, it's available anywhere apart from your exam room. But don't worry, I will supply it in the paper if we need to use it. Okay, that basic equation, I will supply it. That is not basic, so no, I will not supply it. Okay. Now, the same way, we just start to spread it out. Okay. Theta is A, d theta is B. Expanding that term, then we have sine A, cosine B, right? This is A, this is B. Cosine A and then sine B, right? Just put it in according to slot. Nothing complex. However, it's getting very long. I think we should play the same trick again. Consider that the angle d theta is very small. Theta might not be careful, theta might not be, but d theta is small. Well, if that one is approaching 0, the same trick here, nothing new. Okay, eliminate some term. Cosine d theta here is 1. Sine d theta is just d theta. Okay, getting shorter, but it's not really helpful. We can't manipulate it. We cannot use it yet. So if we don't know what to do with it, the first rule of the thumb, expand it and see what we can do with it. So expand the same way. I will not explain it, just time these two into that 2, right? The normal A plus B times C plus D, right? I think you've done it before. So just make it a little bit quicker, it becomes that long. Then again we have repeating. We have minus t psi, we have plus t psi, cancel out. That one stay, that one stay, that one dt times d theta. dt is small, d theta is small, negligible when you time each other. Therefore we have left with 3 terms only. Again we run out of the page, so wipe it out, and then that one from bottom just bring it up to the new page. The same thing, since that one there, last time we have similar pattern, t sine theta d theta and t dt cosine theta last time. Okay, so that pattern would be probably, right? So the same way, we expand it, right? du times v, and then we use the chain rule on that term. We have that. Again, the same. This term the same as that term, this term the same as that term. So substitute for that one, and then move that term into the right hand side. We have this expression. Are you okay with it? Should I continue? Or you need some time to look at it further? We are nearly there. We are nearly there. So come to this. Apparently, in the human sense, in the human wording, it doesn't make much sense, or it doesn't actually explain much. So at this point, we don't explain it by human language. We integrate it. The left hand side is open integration, so it just gets the value we are integrating, right? So if we are integrating left hand side, we just have t psi. Integrate that one, we have the term dx, so it has to remain integration. Notice this is what we call open form. There's no limit. Okay, so when we're going to use it, we're going to use it as normal form. Now if we call that equation 2, there's no equation 3 yet, don't worry about it. Apparently we have equation 1. If we don't want to look at t, there's so many unknown. T we don't know, theta we don't know, so maybe we try to eliminate the term t for now. So I will set up equation 2 and then divide that by equation 1. Okay, so what I should have is t disappear, then sine over cosine become tan on one side. On the other side we will have the integration divided by t origin, to. That to, remember, we already discussed it, it is a constant. Okay, so it can move in, move out the integration as you wish. Okay, now when we look at that, we should realize one thing. I'm not really aware of it or not, but usually if you form the triangle, if that is angle theta, that side will be dy and that side will be dx. Tan theta is actually dy by dx, right, in general sense. Therefore, this tan theta could be in that term. Run out space again. So there we are. going back up. We are nearly there. Bear with me. Now, notice that one then we can integrate it again. If we integrate it, we get on one side y, correct? On the other side, just that integration. Now, this is a general term, meaning as soon as you know the value of, you know the function of w, then you can substitute into that and start integrating. Okay, you have the knowledge, the relationship between x and y, meaning you know the whole shape of the curve. Okay, that is the idea. However, just to make it simpler for us to start studying it, we will assume that, let's say if w is a constant, meaning it distributed equally, right? The normal rectangular box we see, w, okay? Just to make it simpler. Therefore, it's no longer wx, it's just w, a constant. So we will transform that equation. Notice the wording, in specific cases, meaning this proof after this is only for when w is a constant. Okay? Then wx can be changed into w. Integrate, this is just a constant. Integrate it is simple, right? So we integrate it up. Integrate the first time, there is no x inside, so it becomes w times x. Correct? This is open integration. If it open integration, every time you integrate it, you must have a constant adding in. Okay? This one here, I will call it constant number 1, C1, because I will have to integrate it again to get C. Then meaning I will have C2. That term becomes x squared over 2. That term, no x, just a constant, becomes C1x, and last term appear up as a constant, integration on constant. Now this is the reason, specific reason, why they set origin at the lowest point. Because there will be two integration, two constants. Meaning we need two information to eliminate this C1 and C2. So, here is, remember where we set it at? Origin at the lowest point. Don't forget this x and y, what do we set x and y for? X and y is coordination, is point on the cable. Okay? Meaning we have this one here, describe relationship of this curve, the whole curve. Okay? Meaning at this point here, or if we have the slope, we just differentiate that one, we get the slope. Notice that at this point here, we know that x is 0, y is 0. That is the first condition. Correct? But we have the second condition as well, because we set it at the lowest point. Meaning at x0, lowest point, slope must be 0 as well. Correct? It's the peak. So we have the two conditions we need. Okay? So, at x equal to 0, at origin x0, y0. Substitute in x and y, substitute into that. Then we have C2 equal to 0. Correct? Yes or no? Yes. Now, we also know that at x equals 0, slope equals 0. So with that, we use that expression. Right? It's slope and x. Therefore, we also get C1 equal to 0. Correct? So actually, the equation will look quite long. We only have this form. And that describes relationship three-way. xy, which is any point on the cable, and T0, the constant tension, the horizontal tension. At any point, if you take component into x direction, it comes back to T0. And apparently, that's the information we need to analyze every point on that cable. So, let's mark it. This is the benefit of long and difficult proofs. Usually if you go through very long difficult proofs, in the end you get quite a nice simple equations. Usually, not always. However, this subject, as we know, is not about the complexity of equations. It's usually the complexity on how to use it. Okay? So let's see how we use it then. There are usually two kind of questions in this topic usually. Sometimes they give you all the dimensions and apply load. And they will ask for many information including the maximum tension. Or sometimes they don't use the height as the defining factor. They use the maximum tension as the one that is important, as the critical. In that case, it will give you the maximum tension the cable can take, and then you have to find the height, that sum of the heights, these heights. Okay, not that one, these heights, and then start to calculate the others. But it comes from the same principle. Okay, in this case, it is the first case I'm talking about, is that we'll give you all the dimensions plus the apply load. And what we want to know now, the first one we want to know, of course we want to know the maximum tension. Okay, but just to make us understand more on how to use this equation, I also add information about point B. Point B is here, 3 meters from point A in the x direction. The height from that one we don't know. Okay, so that is one thing that we have to find out. Tension at point B, the height h basically divide value of point B, and also the slope at point B. Okay, let's see how we do it. Now remember that equation, that x and that y, as I said, is measured from the origin. The origin is not a fixed point at the moment. The origin is, it's not fixed point from one application to another. Basically at this moment in time we don't know where the origin is. We only know that it's the lowest point. Exactly where, we are not sure. Okay, so the first task is to find that origin. The simplest idea is that we will say that from here to here the origin is equal to something. In this case I use symbol L. Okay, and therefore since the whole span is 20 meters, that one is L, that one is over whatever left from it, 20 minus L. Okay, this one I cannot tell where the lowest point is because there is no symmetry. Okay, if the support level is on the same height, then there is symmetry and the load is equally distributed. Then symmetry meaning the lowest point will be at the middle. You don't need the first step, you can go to the second step. Okay, but anyway, that one, what does this equation mean? Again, this is x, y is coordination of any point on that cable. So we have to look at what coordination that we know. Okay, for example, at point A here, x is measured that way. It has to measure from here to here, correct? The total distance we say is L, but however go that way positive, go that way negative, correct? So x is minus L. Y is measured there from here to here, right? So 6, 6, 12. Substitute into that equation, we have that form, right? Again, it's not enough to solve it, so we look at another point that we know information. In this case, then should be point C, correct? Substitute it, or that equation 1, substitute that one, then x from here to here, well, 20 minus L, going to the right hand side, positive. Y is measured up from there to point C there, 6. Okay, substitute to it. Can I ask you a question? Do we know x, y at the origin? Origin x, y is always 0, isn't it? We know. So why don't we use it? Two reasons. The first reason is, in fact, we did use it. We did use it here. since the proof of the equation, right? So we did use it. We used it beforehand, before we see a problem in the first place. Okay. Second reason why I'm not talking about it is that if I substitute 0 here, 0 here, what I get is 0 equal to 0. It doesn't help. Okay. So it only helps at point A and point C. Now you have two equations. You have two unknowns. Right? One unknown is T naught or TO, T origin. The other unknown is L. Okay? In this form, apparently finding out L is easier. Well, in fact, I used wrong wording. Eliminate T origin is easier. You just set one up divided by the other one. Right? Yes? Okay? So that's what we do. 2 divided by 1. We have that expression. Right? Or you can rearrange it and T equal to something, T equal to something, and then equal them. It's up to you. It's going to end up the same thing. Okay? So let's move it up here. Rearrange it, that one. Rearrange it, that one. How do we solve that form? Take factors. It's a bit tough because I don't think it's actually end up the integer. It might be real numbers. There's an equation for it. This one will not be given. It is so basic that I think everybody should remember it. Minus b plus minus b square minus 4ac in the square root over 2a. Right? Then, usually in this, well, the format is clear. Then we have two answers. Sometimes 1 plus 1 minus, sometimes both plus, sometimes both minus, depending on the case. In our case, it will always be 1 plus, at least 1 plus. 2 plus is okay. But if 2 minus, something is wrong. Okay? Now the question is, we have two values. Which value do we use? 11.72 or 68.28? Why? Because it is inside the range, yes. Because our L is measured from A, correct? Right? If it's 68, it's somewhere here, correct? If it's minus, it's somewhere there. So it has to be something in between A and C, correct? So in this case, that one, there. I have to be precise. If L become minus, it can only happen if you pretension the cable. Meaning you did not look at the curvature like that. You cut it before the lowest peak. Okay, but it doesn't happen naturally. You will have to pretension the cable. Okay? But nevertheless, once we get L, then we can calculate T naught. Correct? There we are. From equation 1, you take that form. We know L, substitute it, then we have that value. Okay? Okay. If because I seen you pull out calculator and you start calculating it. If I make mistake, let me know so I can change it later. Next then. Now the question is not T naught. Look at the heading. I haven't said what we are doing. We are not going to solution yet. At this moment in time, since the first line from the question starting to this line, it just gather information so that we can solve what we want to know. Okay? It's more like geometric solution for now. Okay? So we know equation, we know the T naught. There we are. Partly T naught we already know. Notice the cut here. That cut there has to be at the origin. Meaning I cut here and then I cut at point B. Okay? If I cut the origin, then that horizontal line, that tangent line is horizontal, meaning that T will be T naught. Okay? And therefore is the value we calculated. Notice that this is a three-force system. One horizontal, T naught, right? Then the other one is W coming down, vertical. T is something TB, in this case, in incline. Meaning, in that case, T has to resist both forces at the same time. right? So TB must be the summation of the two, okay? Which means I can calculate that one. Is it confusing or not? I can explain it some other way, but I have to use the board. Is that argument okay or not? So I take it's okay. If not, then you can ask outside. Okay? In that case, if we agree on that one, then we just calculate TB. Okay? So that's our first answer already. Okay? Question number 2 or number B, I'm not sure how I name it, how I number it. I ask for the height and then the slope of point B. That height there and the slope there, right? So there. That is the equation we have. We work out, we know W is 10. We work out T0. So that is the equation for Y. Correct? If we know equation for Y, then we can find equation for the slope. Just differentiate it. X squared, so simple to differentiate anyway. So at point B, notice that it has to measure from here to here. Distance will be 8.72. Correct? But we measure from here to here, that x is minus. Correct? Substitute into that equation, then we should get YB. There. Just plug in calculator, the value of YB come out 6 something. Now, don't forget how we measure Y. Y is measured from the origin vertically up to the point we are measuring. So in fact, that YB is the same value as H. Correct? The slope, still substitute X into that equation we have. So there we are. Minus. It's not what you call surprising, because it's on that side, meaning when you move with X, Y is still reducing. So slope should be minus anyway, right? So that's it. Now maximum tension. Remember the picture? I'll just cut it somewhere. It's no longer at B. Just from origin to anywhere. Draw the one. Okay? The same argument, that T will have to resist that force and that force at the same time. So that T must be equal to that force plus that force. Right? Again, because it's vertical and horizontal, the summation will be in the square form. There. Okay? Notice when we put in that form, that number is a constant, that number is a constant. T only maximum when L square is maximum. We agree? Therefore, we have to find out where is the maximum L square. Don't forget, L is measured from that one, which means origin. Okay? From here to here, the longest on the right hand side, 8.28. That one, longest side is 11.72. Which one? Which one gives you bigger L square? From at point A or at point B? Or at point C, sorry. At point A. The span, if the span is the length, it's not the coordinate. Therefore, it's absolute value. Okay? In this case, as you correctly say that it's that span, 11.72 is the longest. Simple calculation actually. That one, this one here has so many answers. So in summary, let's check the question a little bit so we know we answer everything. Okay? Tension at point B, there we are. The height and the slope at point B, there we are. Right? H is YB, we calculated. And then the last one is maximum tension. And that's the whole complete answers. Again, the calculation, I don't think is that difficult. It's just the picture you see that you have to find out. Shall we have a break? Yes, we shall. See you in 10 minutes. Thank you. Okay, guys. I think it's quite enough today. It's 3:60. So see you guys next week. Okay, then we're gonna go to our favorite topic of virtual work. Okay then. Yeah, it's lab. Okay, then see you guys next week. Okay, and if you have enough time, I will come up with some games to play. Okay. See you guys next week.